Hi students, in this session we will discuss about types of photodiodes. Basically the photodiodes are of two types. First is the Pin Photodiode and second one is the Avalanche Photodiode. In this session we will discuss about Pin Photodiode. So explain the physical principle of Pin Photodiode. First we will go to the Pin Photodiode structure. Basically, the pin photodiode is a diode and that has got a wider undoped intrinsic semiconductor region between a heavily doped p-type semiconductor and n-type semiconductor material. And the p-type and n-type regions are heavily doped because they are used for ohmic contacts. The wider depletion region is formed between the p and n layer by a lightly doped n-type material, and we can consider it as an intrinsic material. So this structure forms a PIN or pin structure, and this is the structure of the Pn diode. You can see that here the P and N regions are heavily doped. P and N regions are shown as P plus and N plus regions, and metallic contacts are taken here for taking the connection from the P side, and from the N side the connection is taken from here, and the intrinsic material that is made up of lightly doped n-type material that is shown as I. So this structure forms the pin or PIN form. So here the depletion region between the P region, P plus and N region is shown like this, and here the width of the P region and N region is very small comparing to that of the intrinsic region. So now let us go to the working of this pin photodiode. So usually the pin photodiode and which will be reverse biased. So this is structure, and here P and N regions are there, and intrinsic region is shown by I, and P region and N region is heavily doped and its width is very small comparing to that of the intrinsic region. So when we are applying a light wave here, that is has an energy h nu, and this light will be absorbed, a major portion of this light will be absorbed in the intrinsic region. So the absorbed light will causes the generation of the electron hole pairs in the intrinsic region. You can see that P region is connected to the negative terminal of the battery and N region is connected to the positive terminal of the battery. So it will be reverse biased. Once electron hole pairs is produced in the intrinsic region, they will be move according to the electric field. So that means there is a drift of the carriers from the intrinsic region, that means from the depletion region to the respective N and P region. That means electrons will be moved to this side under the effect of the electric field. So there is a drift of electrons from the intrinsic region to the N region, and similarly there will be a drift of holes from the intrinsic region to the P region. That means there is a drift of holes from the intrinsic region to the negative terminal. So this constitutes a photon current. That means the incident photon will be converted into the electric current in the outside circuit. So here also there is a chance of diffusion. See, when a light of energy h nu is incident here, and that will produce as a electron hole pair in the P region, similarly in the N region also, but you can see that the width of the P region is lesser comparing to the intrinsic region. So the chances of producing the electron hole pair comparing to the intrinsic layer in the P region is lesser. So the holes or so see here the electrons produced in the P region will diffuse from the P region to the intrinsic region. See here we are using the term diffusion because here the movement of the electron from the P region is due to the changes in the concentration in the P region and intrinsic region. That is why we are using the term diffusion. So the chances of diffusion current from the P region to the intrinsic region is less because its width is lesser. Similarly, the holes, in order to constitute the diffusion current, the holes in the N region should have to move from the N region to the intrinsic region, and that holes should move to this side in order to provide a drift current. So the chances of diffusion current is lesser in this structure of diode. That means in pin photodiode, the chances of diffusion current is lesser comparing to the drift current. So we can say that the photons absorbed within the depletion layer or intrinsic layer generates electron hole pair, and those charge carriers will drift under the influence of the electric field, and this constitutes the drift component of the photocurrent. And here the diffusion component of the photocurrent is less due to the smaller width of the P and N regions. And the equations that is relating and the pin diode structure is, first one is the depletion layer capacitance, and the depletion layer capacitance is given by the equation C is equal to epsilon S divided by W, where epsilon S indicates the permittivity of the semiconductor and W is the width of the intrinsic semiconductor, and A is the cross-sectional area. Next is the transit time or drift time for a charge carriers generated at the edge of the intrinsic layer is given by the equation tau drift is equal to W divided by V drift. W is the width of the semiconductor and V drift is the average drift velocity. And the maximum 3 dB bandwidth of the photodiode is given by B max equal to 1 by 2 pi into tau drift. We can substitute for tau drift as W divided by V drift. So we will get maximum bandwidth B max equal to V drift divided by 2 pi into W. And the maximum, if we are giving a light of step input, then the maximum response time is given by 1 divided by B max, where B max is the bandwidth. And similarly, if you are giving a step light input to the photodiode, and the time taken for the response to increase from the 10% of its value to the 90% of the value is rise time, and that rise time is given by the equation TR equal to 0.35 divided by FC, where FC is the cutoff frequency.